let's get started. I'm going to start by reviewing part of what we did last time. So it was at the end last time we talked about things, architectural features that improve SGD. So what we're going to do today is talk about developments up to 2015. So bring us up to 2015. These are things that did make a big difference at that time, and they're still important for the most part. So we talked about ReLU many times. This was the first innovation that it was important in AlexNet in 2012. I sort of want to go over this again to talk about why we have these problems with deep networks. So one thing that happened between 2012, the start of the deep revolution, in 2015, is the networks got deeper, a lot deeper. AlexNet, I don't know, it was 5 or 6 layers. By 2015, we were training 100-layer networks. So what developments made that possible? And why is it hard? Why is it hard to train a deep network? I showed you this monster, the Inception network, that had 3 heads in it. And had 3 heads in it to get around this problem with deep networks. So what I'm writing on this slide is just a simple weight feature inner product. Right? What happens in a linear threshold neuron when you multiply values that are coming up from below the neuron with weights at that neuron? So I want you to think about deep networks. This is the weights in some layer in the deep network. This is the values being brought up to that layer. And if the weights are too big, say they're such that this value is twice as big as that value, and as you go up the network, you're going to get this exponential explosion in the values. If this value is half of that value, then you get this exponential decay of the values as you go up the network. So it's not just a problem with the question.
So when this is a problem because we're using ReLU in some sense, because we're not saturating it. Like if we're doing sigmoid, this wouldn't be a problem.
If we were doing sigmoid, they would not explode.
Yeah.
The gradients would just disappear because you'd be on the, so we'd have a disappearing gradient problem. So people use ReLUs. So yes, ReLUs let things explode and so if we think about this inner product, if we think about backpropagation, there's this nice swap rule for backpropagation. If I want to know how the loss, the gradient on y, influences the gradient on the weight w, right? I just use the swap rule. So the gradient on w is, you add into it for this particular addition, the gradient on y times x. The point here is that as you're backpropagating, if the values are exploding, the gradients are also exploding. So you get a gradient explosion problem. Okay, and we done. Yeah.
For exploding gradient, you mentioned that next time it will double
As you go up the network.
Oh, but if the next layer the weight is small, wouldn't it not double?
Yeah, I'm just saying if all the weights were doubling things, you're in big trouble. If all the weights are having things, you're in big trouble. So the question is, so what I'm going to talk about next is how do you initialize the weights? It's initialization. How do you initialize the weights such that things remain, order 1 all the way up through a deep network? So what we're going to do is try to initialize the weights at the layers such that the values, such that they're like Goldilocks weights, right? The values are going to be order 1 all the way up. And we talked about this last time, but I stumbled over my words and it wasn't very clear, and I fixed my slide, so I want to do the new slide again. So we've got this weighted sum, right? This is the weighted sum that's inside a neuron, a linear threshold neuron. And what I want is if x is order 1, then y is order 1. I want that to be maintained as an invariant as I go up. So the solution is this, the Goldilocks solution, we assume x is order 1, is to set w for the solutions that is used is you draw a W randomly. This is going to be a random initialization. You draw W randomly from a Gaussian whose standard deviation is 1 over the square root of n. And then if you make an independence assumption, you're adding n terms together. And so that's going to expand, if that's going to multiply whatever the variance of this is by 1 over root n, by root n. And so with this initialization, if we assume everything is independent, this comes out being order root n. I should have said what we're really aiming for is 0 mean and order 1 standard deviation. So we did this last time. Any questions about this? Batch normalization. We did this last time too, but I wanted to, I sort of reworked these slides, and let's do it again somewhat quickly. So, what I did to rework these slides is to put this in the context of convolutional neural networks. So I'm going to define 3 forms of batch normalization, all within the context of convolutional neural networks. So a layer in a convolutional neural network has this shape, right? It's got a batch index, a position in the image, an XY position in the image, and the response of some set of neurons at that position. We did this last time. Now, one thing I think I could have made clearer is that the same neuron, what do I mean by the same neuron? Consider index 32. This is a tensor, it has indices, consider index 32 in the neuron index. That neuron has a value at different places. Neuron 32 is that neuron, 32, has a value at every place in the image. So you can think of it as a procedure that's being called in many places of the image because the weights in how you compute that neuron are the same every place it's used. Right? That neuron is defined by its set of weights. And but we're using it at many places in the image. There are many occurrences in the image, depending on X, Y, and depending on the batch element. Okay, so in sort of the simplest formulation of batch normalization, what we're going to do is we're going to normalize we're going to normalize over the batch for each position this neuron is used. So I'm going to take a position in the image in that neuron, and I'm going to average over the batch the neuron response at that position. Does this make any sense? And then, so I take that average. I also compute a standard deviation over the batch, and then I subtract the mean and divide by the standard deviation and get a normalized value. We did this last time. Spatial batch normalization. This, I think, maybe was something that was less clear. Okay, now what I'm going to do is here I computed an average that for each x and y, each place that neuron was used, I computed a separate average, and I only averaged over the batch. But if it's neuron 32 and it's using the same parameters every place it's used, it seems better to average both over the batch and every place it's used for that neuron 32. Right? So now I'm going to average over the batch and every place what neuron 32 does, its response. Right? And then I'm going to take that standard deviation and correct for that. Okay, this makes a lot more sense. But it's still averaging over the batch. And the most recent development was layer normalization. So layer normalization does not average over the batch. It averages only over the different occurrences of the neuron.
It's just to be clear, if we fixed B and N and we let X, Y vary, is that like not? Would that not be like the quote unquote like layer of the current neuron and after like what? So
I think you're asking about the next slide.
Oh, okay.
So we fix B and N, and we compute for a given batch the average over all the places it's used. That's layer normalization. And the advantage of layer normalization is that, an advantage of layer normalization is that you don't have to, at test time you only have one batch, one image. So there's no way to compute the batch. Batch normalization isn't meaningful at test time. But this is, because you're averaging over the positions in the image.
I think what was being said was we're solving over the batch, so on the left hand side it should depend on the batch anymore.
Is there a typo?
Yeah,
Which, this slide?
layer normalization. Oh, the next slide. Yeah, the very first equation. It's probably a typo. LPN, whereas on the right side, we're summing over the batch as well, so B should disappear.
Ah, yes.
Yeah.
That's a typo.
So on the left hand side, the B should be there, right?
Right.
Okay.
Good.
Yeah.
Thank you.
Like, I'm a bit confused. The B should be there, but in the summation you shouldn't sum over B, right?
This should only be XY.
Yes.
Not B.
Oh,
That
okay.
B is
I
wrong.
see.
If we're doing like one of these batch or layer normalizations, then do we need to do the initialization?
You
It
typically
seems
do
like
both. I mean, in principle, this would correct for
any initialization.
in the initialization, right? But you typically do both. I mean, there's one more thing to add here, and that is, there's a good reason to do. No, you're right. I mean, this would correct for it, but typically people do both. I don't know why. Okay, here's a strange thing about batch normalization. All of these forms of batch normalization add an affine layer after the normalization. So after you've normalized it, you introduce two parameters which rescale it. You just scaled it down to one. Now you're going to rescale it by some scale that's a parameter, and you're going to add some bias term. The bias term is initialized to 0. And now you're going to learn the new scaling and the bias term. Right? And it can, in principle, completely undo the batch normalization. Because that's all the batch normalization is doing, is applying an affine transformation. But these additional parameters seem to make the SGD more efficient, and it does make it less sensitive to what's happening at the layer below. So it does change SGD and seems to be useful. Okay, residual connections. This is 2015. This residual connections are fundamental to deep learning now. Every architecture uses residual connections. It's not on this slide, but there was sort of a tension on credit because Schmidt-Huber published something called highway architectures or highway networks that were very similar to skip connections. There's this highway view. So what is a residual connection? It's also sometimes called a skip connection. I've drawn this picture upside down. The data is flowing from the top to the bottom. Okay, and what we're going to do is we've got a value, some layer coming in here. We process the layer, like this is a convolution in a ResNet. We put it through a convolution, and then we take the result of that convolution and we add it to the input. And that's what goes down the pipe. And so why is this a good idea? Yeah.
So is it literally the input or is it like a scaled version of the input that goes into the edit?
In ResNet, we just add. I mean, if this ends in a batch normalization layer,
Yeah.
that has a scale in it. Right?
But this guy, the one that's going straight through, not getting convoluted, is being added straight without any scaling.
Right,
or also.
but whatever computed it could have added a scale to it.
Adding, you mean literally summing it?
Literally summing. Two tensors are taken, it's arranged such that those two tensors are the same shape. You just add them.
They are correlated, like the first input is summed with the first output of the convolutional network.
So where does the term residual, I'm not sure this is going to answer your question, but in linear regression in statistics, you'll have a model, and that model will make predictions, and there'll be a residual error, right? For each data point, there'll be the difference between what the model predicted and the truth. So the intuition is this is sort of this residual connection is attempting to correct that model. So what you're going to do is you're going to add the residual to that model's prediction.
Basically, you add the error.
There's no, the error is way down here. And there's an error gradient that comes back to here. Right, so this thing is going to be trained to improve the final loss, but it's just adjusting this between here and here. But this is literally just adding the two tensors together. Okay, why is this, or how can we think about this? A fundamental problem in deep networks, remember that inception network that had these three heads? Those three heads were in there such that there were heads close to the input. And that head close to the input is providing a gradient path that's not going through so much network. Here, if you just look at this path, basically you're summing up all these residual computations. So there's this big sum. And one term in that sum is the input. It's sort of the input layer, or something very close to the input. So if I've got a loss down here, there's a direct path. The SGD is making a direct path right to the input. So that is what's making this trainable, right? The gradients go back much deeper. So this is ResNet, residual connections and CNNs. What I've written here is just, this is a conv layer, but I'm not calling this the next layer. This is going to be like the residual connection. So you just, in a framework, you just call conv, you give it the kernel, you give it a bias term, and you give it the previous layer. And this will return an object with a value and a gradient features. Okay, then I take this thing that's produced by this convnet, and I simply add what the convnet produced to the previous layer, and that becomes the next layer. And I'm using this convention here where capital letters are, I'm denoting the whole tensor.
Professor,
Yeah, there should be some questions here.
how do we make sure the shape is the same if n in n and now it's different?
That's the question, right? So here I'm assuming that the shape is the same. And typically you typically do have many layers, especially in very deep networks. You have many layers that are the same shape. So ResNet is like 50 layers deep, but it's only reducing the spatial dimension, maybe 4 or 5 times, 3 or 4 times. So out of those 50 layers, only a few of them are not the same shape. So for this to work, this n in and n out have to be the same number. And the spatial dimensions of the kernel have to be, the spatial dimensions of the image and the kernel have to be the same.
So we don't need any sort of regularizing term for our residual connection. We usually just dry to sum it up with.
You just sum it up. But if there's a normalization layer, that normalization layer includes an affine transformation. So I didn't put a normalization here.
Oh, okay.
But I could. I could follow this conv by a normalization layer. That normalization layer has a affine transformation on it. All normalization layers end in this affine. So that can set a weight. Right? There's a trainable parameter there, so it can learn how important this layer is. Typically in ResNet, we apply this residual connection across a couple convolutions. So you'll do 2 convolutions with no residual connection and input residual connection around both. So I've just written out that equation here. Compute a layer at L plus 1, a layer at L plus 2, and then you take the layer at L plus 2 and connect it to L. So you're going around 2 layers.
So if we want to reduce the dimension of the output, we can use residual.
Handling spatial reduction. Last year, this slide was much more complicated, but the right way to think about this is you have a spatial reduction layer that doesn't do a convolution. So I can subsample, downsample the spatial locations. And typically when you downsample the spatial locations, you introduce more neurons. Right? So the spatial dimensions are cutting in half, the number of neurons is doubled. So what you do is you can simply downsample, right? Downsample, you just take a checkerboard pattern and compress it, downsample the layer, and pad zeros into the extra neurons. And do that, and there's no convolution there, right? You're just downsampling and padding with neurons. So the convolutions are below that. I mean, the skip connections go below that and above that. So this you don't need a skip connection around the downsample.
Yes, sir.
Yeah.
Back 2 slides, I wanted to ask you something. In the slide before that we skipped, is that L in the second line supposed, or the second equation?
Yeah.
The L sub L plus 1, is that supposed to be L twiddle? Is that L from the first layer, or how does L twiddle L plus 1 get used?
L twiddle L plus 1. Oh, there should be. I introduced typos. This should be L twiddle. And this should be K L plus 2. Okay. I'm dyslexic. These typos drive me nuts. Okay. So this is showing ResNet 32. This is 32 layers. Colors, I think, are representing information flowing from the top to the bottom. Colors are representing changes in spatial dimension.
The residual connection being added after every 2 was just made up, right? Like they could have done 3 or something.
They do. They did 2 in ResNet 32. In ResNet 52, they did 3.
Okay.
I've lost the slide. Oh, here it is. Another thing that was done in ResNet 52, the deepest version, is bottleneck layers. What's a bottleneck layer? So as the number of neurons gets large, when you do it, the kernel is considering every pair of an input neuron and an output neuron. Right? So the number, if you're dealing with 1,000 neurons, that gets to be a lot of neurons. And you're doing it for a 3x3 window. All of these convolutions are 3x3. So to make things run more efficiently, what a bottleneck layer does is it takes this thing with a large number of neurons and it compresses it to something with fewer neurons. Okay, so what we're going to do here is a convolution. This is a compression convolution to reduce the number of neurons. We compress down to a number of neurons in the bottleneck. It's a bottleneck, so it's using fewer neurons in the bottleneck. So here, n bottle is smaller than n in. It might be a factor of 2 smaller or more. And when you're simply compressing the number of neurons, you're simply taking each position and independently compressing its number of neurons. So you could write that as a 1-by-1 convolution. Right? A 1-by-1 convolution just looks at the place in the previous image. So this 1-by-1 convolution reduces the number of neurons. Now we've got a layer with fewer neurons. We do our 3x3 convolution there. Right? right? And because it's small, because it's quadratic in the number of neurons, we're getting, if we cut the number of neurons in half, this is only going to take a quarter as many multiplies. So this could be a significant reduction. Then we do another convolution that blows this back up to whatever the pipeline number of neurons is, right? So you reduce it, you reduce it with a 1-by-1 convolution, do your 3-by-3 convolution, and expand it back. Where each of those are, these convolutions are basically just a multilayer perceptron at each pixel.
And doing this doesn't sacrifice any sort of effectiveness,
There's always somebody.
or is like
A
is the trade-off worth it?
A question came up the other day. Somebody asked if reducing the number of parameters was a good thing. Well, everybody's heard that in scaling we want, we've got a trillion parameters or whatever. So it seems like improving the number of parameters is a good thing. You want to get a lot of bang for your buck, right? So I can always make this model bigger. And the idea was this gives you more bang for the buck. When you compare architectures, it's important to compare them at a similar number of parameters.
So there is probably a step down in terms of how effective it is, but it's worth it for the.
So if you fix the number of parameters, you say you've only got so many parameters. The idea is for a fixed number of parameters, this bottleneck layer is going to help. That's the idea.
Just to so the KUKR could be like MLPs, which are supposed to reduce somehow an infinite model. I'm a little.
This KU here is a 1-by-1 convolution.
I see. And that's how are we applying that convolution? I guess I'm just a little confused. Because NN is all of the neurons right on the input, right? And we want to get to N model, but are we just assuming that the convolution is doing that?
A 1-by-1 convolution. Well, convolutions in general can change the number of neurons.
Yeah.
In arbitrary ways. A 1-by-1 convolution says the output, the value of an output neuron at a certain place is determined only by that place on the input.
I see. Okay.
So you're compressing at each place. You're compressing the number of neurons.
Are there typical guidelines for how much shrinkage you want across the bottleneck, or n bottle over nn? It's half.
I'm trying to remember what ResNet did back in 2015. I think it was half, but I'm not positive about that.
I don't get why we added that extra bottleneck. What does it do for us?
It just this way of computing the next layer, the bottleneck, has fewer multiplies.
I mean, it's faster.
So it's faster.
How should I think of the intuition of reducing something and then blowing it up again? Because my impression was based on experiments. If you
think principal component analysis. So if I have a matrix, I can compress it, and that matrix has eigenvectors. Most of the information is going to be along the dominant eigenvectors when you apply that matrix.
then would there be no need to blow things up again, because it sort of feels like I'm throttling the information progression through a bottleneck, and then even if I expand it later on, even if there's more degrees of freedom, the information is already been lost in the projection because of the bottleneck. And so maybe
Well, the one thing that's happening here is you don't really understand what these convolutions are doing. We don't understand these networks. Right? So the idea is that there's going to be certain dimensions that are important to this computation.
Okay.
So we'll shrink it into the dimensions important to this convolution, do that convolution, but then we've got to push it back because it needs it in the next layer at a higher dimension. So the general picture of residual connection is very simple, right? We've got a layer X. We're going to compute from X a correction, a residual, add it to X, and that'll be the next layer. So it has this very abstract formulation. Okay, recurrent neural networks. So in 2015, these are a big deal. They're sort of not a big deal anymore, although I think they're still used. Somebody told me that Google Translate uses an RNN to generate the output of the translation because it's faster, it's more efficient than a transformer for that. I don't know if that's still true or not. But it's something, you know, of course in deep learning we have to talk about RNNs. It is a conceptually important thing. So what is an RNN? So they were typically used in, or are typically used in language. It's a way of building a language model. So in language you've got a sequence of, or any sequence data. Like you've got a sequence of words or a sequence of tokens. It could be of indeterminate length. What I'm going to do in a recurrent neural network, so this is going to be the same neural network used across time. It's recurrent because it's feeding itself. So a recurrent neural network is this network A that looks at the first token and produces a hidden value. That hidden value goes, a network value, some vector. That vector goes across to the next unit that looks both at the input and this next vector, this next hidden vector, and just keeps going. This is the same network repeated over and over again, a recurrent network. Now in principle, this network could remember a state, right? It's got a hidden vector. It could remember state in that hidden vector. So it can remember information about what it's seen along the way as it's computing. And in principle, even simple perceptrons, multi-layer perceptrons, even one-layer perceptron in some very dubious formulation is universally expressive. So if this thing is universally expressive, it can be, computing anything that's a function of the entire sequence. However, there's something called a vanilla RNN. This is a vanilla RNN. So I've written what this box is in one equation, right? The box has to compute the next hidden state, the next state that goes across here from the previous state. Let's look at what this box is doing. It's computing the next state that's going across from the previous state and x. So the next state, ht minus 1 of, after this lecture, this batch index is going to disappear. I'm still using the batch index. Ht plus 1 of the batch index and some number of neurons, this is the dimension of the vector, is going to be some activation function, maybe a sigma weight or a ReLU, of two weighted sums. There's a matrix that takes a weighted sum of the previous h, and another matrix that takes a weighted sum of the incoming x, compares that to the threshold, and then passes it to a sigmoid, and that gives us the next hidden state. So it's got a matrix depending on the previous state, and a matrix depending on the next input. Question?
I guess I'm kind of confused by your diagram because are we using H to mean like the hidden state that's getting passed along? Why is that
The
being like,
diagram
kind
is
of
confusing
output?
because it's got H coming out here and coming out here.
Okay.
Now, in practice, the slides on this have disappeared, but in practice, this can be stacked, right? So I could take another one of these and put it up here, taking this sequence as the input. And in practice, they were typically stacked. You can also run one forward and one backward, and concatenate the forward and backward value at each position. So each position is a pair of forward, backward value, and they're stacked. There's an analogy between an RNN and a deep network, because the computation here is deep, right? If you've got a loss function coming back down from up here, there's a loss function affecting this output, it's got a long way to go to affect, to correct something that happened down here. So there's a kind of conceptual analogy between the time progression here and deep networks. And the big innovation was something called gated recurrent neural networks. So a gated recurrent neural network has something analogous to a residual connection. Okay, so I've gotten ahead of myself a little bit. This is just to point out that this problem with exploding and vanishing gradients are happening in RNNs because of the time. For example, if the weights are too big, as you go forward in time, things will explode. And if they're too small, as you go backward in time, things will explode. So there was this thing called gradient clipping. So the gradients would get big. The gradients coming back, because they get multiplied by values all the way back, they would get to be enormous. So what they would do is clip them. So there would be a clipping parameter alpha. And if you had a weight whose gradient was, this is a weight vector. If the weight vector had a norm that exceeded alpha, you would divide by its norm. That should be alpha, so that it was capped at alpha. That Nmax should be alpha. We're talking 2015. Okay, I've said this already. Time as death. So what we're going to do is introduce something analogous to skip connections, but through time. So here is a gated RNN. So what is a gated RNN? So this first equation is the same equation as I had before. What this does is it computes a vector by looking both at the previous hidden state and the incoming x. Right? I'm using this Einstein notation for just a matrix times a vector, and comparing it to some pressure. These are both computed by the same formula, but with different parameters. All right, so I've got a gate, this is going to be like a residual connection, that's why I'm calling it R, and I've got a gate. And the residual connection in gated RNNs are computed with tan H. Tan H is like a sigmoid, except instead of going from 0 to 1, it goes from -1 to 1. And this is done with a sigmoid. Now that is a sigmoid, so this gate is between 0 and 1. And then what you do is you take the output. This is the residual step. You take the output to be the gate value times H plus 1 minus the gate value times R. So people kept asking, is there a weighting parameter in the residual connection? Do you say, do I weight the two things in the sum? Here, there is a weighting, but it's computed as a function of your inputs, of your previous state and your input x. Right, so we compute a gate value between 0 and 1, and then we use it to form, it's between 0 and 1, so we use it to form a convex combination. It's the gate times H plus 1 minus the gate times R. Question?
So since this differs across layers, this means that every layer has a different weight regarding its gate and its residual.
Well, the weight, as you go through time, the gates are being computed at each step.
And they're going to be different, or see different across each one.
They're going to be different. They vary with time because they're being computed. But like in a CNN, each layer has its own parameters. Right here, you're using the same parameters at every time step, but you'd like it to behave differently at each time step because in a CNN, in some sense, you're getting different parameters. Here, instead of getting different parameters, we get different gate values, which says how much do we weight the previous value and how much do we weight the next value. And this weighting is different at each feature. Right? So for each feature, we're deciding, do we preserve that feature from the previous time step, or do we replace it with something from X? And this can be written as in terms of a Hadamard product. So this Hadamard product takes two vectors, and there's capital notation to mean the vector, it's just component-wise multiplication.
Why do we use the activation function here? What's the
Yeah, I don't think I have a good answer for that. The intuition was that the information carrying signal should be able to be positive or negative. But the gate want a convex combination, so it has to be positive. So yeah, the shape of the activation function is a little, people play with it, and the deep learning networks seem to be able to adapt to what you use. For some reason, the signal that's being, the residual part, people wanted to allow it to be negative. That way, when it reaches some neuron, it can vote against it. Okay, this is the simplest one. There were others. So this is a GRU. It's a little bit more complicated. I won't write out the equations for it. This is an LSTM. Schmidhuber, who did the highway networks, you probably all know who Schmidhuber is. He's the fourth horseman of deep learning, who did not get the Turing Award. He's really pissed off. He's kind of a inflammatory person. I think it was just because he was nasty that he was not included. And I mentioned before that he did highway networks, which were done about the same time and had about the same intuition and structure as residual connections. LSTMs were from the 90s. And LSTMs were the first gated recurrent neural network. And in 2015, LSTMs were huge. Google was using them, everybody was using them. The transformer had not arrived yet. So this was the way of processing language. And Schmidhuber made a big, it was true. He predicted this in like 95.
Does the X there is that a Hadamard product or is that just a what?
These product things are Hadamard products. This is just data path. So back in the day, we had class projects on GRUs, on gated recurrent units, and people found that many of these different architectures were all sort of equivalent in their ability, in their performance. And there's this paper that came out that said the really important thing is how many parameters they have. So you don't want to compare different architectures with different numbers of parameters. The number of parameters sort of predicted their performance. Okay, I'm way ahead of myself again. Any questions now?
Yeah, so you clear the outputs, the H's, those are like high dimensional, and then you need some network to turn that into like a word you're translating.
Yes, right. There would be, we take a softmax over words at each output position. I'm going to talk about that. We're going to get to language. We're going to do language next.
Page 24. Skip connections. Isn't that we have to handle the fact that the same model parameters are used at every time? So that I don't get this sentence.
So in a CNN, in ResNet, right? ResNet is a residual CNN. Each residual correction has its own parameters, independent of all the other parameters. In this, in an RNN, each step is using the same parameters. Because the network is...
How is it related to skipping these connections?
So when you do the gated version, you've got this addition right here. And that addition is analogous to the residual connection. But here you want to do more computation because you're forced to use the same parameters every time. So the parameters are they're basically computing what information to hang on, what information to preserve from the previous layer, and what information to replace from the incoming X. And that gets computed as you go. And it's making, I think, the way I understand it is it's making up for the fact that you don't have separate parameters at each step.
How do you initialize the original hidden state? And is the original hidden state a learned parameter?
You can do that, but I think it works, but people typically just make it 0. All right. Now for the fun stuff. Language modifier question.
It seems like from the way the LSTM was built is like you can take your favorite like control theory architecture and just go ham with randomly adding how far back you go. Like, is there a method to this madness of how far to go and what to connect to where? Or
Well, I think the deep community is very enamored with universality. So the idea that, you put something in there that in principle could do arbitrary computation and you let it figure it out. Right? And there's this bitter lesson blog post, have you heard of this? It says that the more insight, the more you try to understand your domain and build it in, the worse your system performs. You're better off using a universal architecture and letting it figure it out.
so in terms of representation, like grooves and LSTMs are equally good for a given number of parameters? Or?
Grooves and LSTMs are very comparable. They're both just universal and they both have this ability to pass things through. I was talking to someone proposing some architecture and he said, well, if you get the architecture, if you just make a bug, you don't type it in right. Deep learning will overcome the bug. And you'll be fooled, you'll think it works. Okay, language modeling. I don't know if we're going to get to the transformer today, and I'm not up on these slides, so we'll see how it goes. So we may get to the transformer. Language modeling. All right, I said before, so what's language modeling? I'm going to present this in the terms of individual sentences, because it's just conceptually easier. Modern language models take a block of text and just have a fixed length, and they ignore the fact that they ignore where the parentheses are. But I'm going to present it in terms of sentences just because it's easier, and there are reasons to think about that. Okay, so what is language modeling? I have a probability distribution over sentences, right? So this is the case where we're trying to model a probability distribution. So this is the unconditional case of the fundamental equation. Right? I said this is exactly this unconditional case of the fundamental equation is exactly what trains the base model in GPT-4. So if you remember, we're trying to set the parameters of the model to minimize this log loss, where we want to compute the probability of, we're drawing a sentence from the population, and we want to compute the probability that the model assigns to that sentence. And we want the model to be faithful to the actual probability of the sentences. Shannon was interested in the entropy of English. Right? He was interested in communication. It's Shannon's general capacity theorem. He said, what is the entropy of English? And he actually did experiments where he had people predict the next character. And he produced bounds on the entropy of English based on, people are terrible at that. They're meaningless. So it's a general theorem, and I should have done it earlier, that if you assume universality, if you assume your model can model any distribution, then the optimum of this function is exactly the population distribution. So under a universality assumption, this will converge on the actual population. Okay, but how do we compute a probability distribution over a sentence? Because the sentence might have, New York Times averages 25 words. So that's a very unlikely sentence. It's 25 words long. How do you compute that probability? So we're going to assume, these days people talk about tokens. In the old days, people would talk about words. Think of tokens as like words. But you use tokens because if you've got a name in a foreign language, that's not going to be in your a priori vocabulary. So you can break it down into little few character chunks that are in your vocabulary. And those are called tokens. So we're going to let W be some finite vocabulary of tokens. Think of them as words. And a sentence then is going to be a string of these tokens. This W star just means all strings. And then again, we have our fundamental equation. So to get this probability of this sentence, we're going to do an autoregressive model. So autoregressive models are a big deal, not only in language, they're currently a big deal in vision. I mean, we'll get there, where you predict one pixel at a time, intuitively. So what's an autoregressive model? An autoregressive model predicts one piece at a time. And it predicts it given the pieces that it's seen before. So I'm going to take the probability of a sequence of tokens or words to be just by the chain rule, the probability of each word given its preceding words. Right? And this is making no assumption about the distribution. It's just the chain rule. We're going to assume an end of sentence token. So if we're modeling sentences, in order to get a well-formed distribution, it's going to be a distribution over sentences of different length. So the idea is when there's a certain special token called the end of sentence token, and when the model sees the end of sentence token, the sentence is finished. So if you have a generative model, if you're talking to ChatGPT-4, it will decide when to stop spouting. There's a little button you can click to make it stop, but the way it decides to stop is the generative model generates an end token. It says, I'm done. And so we get a probability distribution over strings under the assumption that every string ends with an end of sentence token. Standard measures of performance. So there's various ways to measure, there's various units in which you can state this log loss. So for language, there are a couple standard ones. One is bits per character. So you take the log 2 of the probability. That's a number of bits. Log 2 of the probability is a number of bits. Every factor of 2 is a bit. You take the number of bits it assigns to the sentence, and you count the number of characters, and you divide the number of bits by the number of characters, and you get bits per character. Perplexity is a token level or word level measure. You do the same thing, but instead of dividing by the number of bits, you divide by the number of tokens. And then typically you take 2 to that. So the perplexity is 2 to the number of bits per token. Back when I was at AT&T, I would have these yelling matches. It's my fault. I like to yell. About things like whether simply modeling the distribution of English could reveal the semantics of English. Nobody believed that, but I was a big advocate of that. And I would yell at people. And at that time, so this was in the 90s. At that time, perplexities were about 60. And when people talked about language models they were thinking about superficial properties, like what words follow what words. They were these n-gram language models. So it made it very hard to believe that language modeling would ever uncover semantics. But the perplexity stayed at about 60, well into the deep revolution. And now, I don't know what GPT-4's perplexity is, but they're under 10. So the progress in perplexity has been enormous. That's what I just said. Now, the deep revolution is finally question.
How do you know it's less than 10?
People report it.
That if you take a big enough chunk of like English text and just try to compress it, like how many bits per characters would you get?
So we're gonna do some information theory later in the course, but there's a theorem that says that the optimal compression is the entropy.
Yeah, but I was just asking how much, because it has to
So
be.
in principle, when you're down to let's say complexity of 10, that's like 3 bits per word. So you should be able to compress it to 3 bits per word.
Yeah, so I guess we should compare the 10 against that number, right?
Against what GZIP does.
Yeah.
So GZIP is not as good, not nearly as good as modern language models. Machine translation and attention. So we have our notion of autoregressive models. So we've talked about this before. This is just a loss function. I didn't talk about sampling. So one thing that's important about an autoregressive language model is that it both computes a probability. There's 2 things you want from a model. You want it to be able to take a sample and compute its probability. The model wants to be able to compute the probability of a sentence. You also want to be able to draw a sample from the distribution that the model defines. Right? And the nice thing about autoregressive models is that they can do both of those things. Right? I can take, by this chain rule expansion, I can get a probability for any sentence, and because I'm generating a distribution over tokens, I can generate the tokens one at a time and generate a sentence. So GPT-4 can both compute a probability of a base model, it can do a probability for a string, and it can generate a string. So in machine translation is now a labeling problem, right? You're given an English sentence and you want a French sentence. So it's a conditional, now we're working with the conditional entropy. And the big, I've already talked about this talk from Ilya Sutskever in 2014, where he said minimal innovation for maximal effect. And this was the paper, right? It's a sequence-to-sequence model about translation. This is before transformers. So in machine translation, it's a conditional model, and so this is just stating the objective function for a conditional model. You want to maximize, you want to model the probability of the French given English. Okay, what they did, they were using RNNs. So Ilya Sutskever, minimal innovation for maximal effect. At that time, everything was an RNN. We're going to take an English sentence in this work and compute the thought vector. So a thought vector is a vector that represents the sentence. And this really weird thing happens, right? You take English, you compute a thought vector for an English sentence. we pass the thought vector to a generating model, and it generates the French. And there's a famous quote, I'm blocking the name, but people got very upset. I was very disturbed by this, that you could compress a sentence to a vector and then just decompress it into French. And Ray Mooney was quoted for, I don't know, 4 or 5 years as saying you can't compress the meaning of a bleeping sentence into a single bleeping vector. Nobody quotes him on that anymore because it seems to be true, or at least it's not as shocking anymore. Okay, so how do you compute a thought vector? So they computed in this paper. They ran an RNN backwards over the input. And why? And it was actually important that they ran it backwards over the input because that means that the last input to the thought vector was the first word of the sentence. Back, so the beginning of the sentence is freshest in the thought vector. And then when you decompress the thought vector, you're decompressing the first words. And English to French, the word order tends to be somewhat reserved. So you're generating, you want it to be generating the first part of the sentence as it's generating French. So we're going to take this thought vector and we're going to use it instead of generating. There was a question about how you set the first hidden state in an RNN. You're going to set the first hidden state in the RNN to be this thought vector for the English. And then you're going to use this RNN to sample sentences. So it's going to be a network that takes one of the hidden vectors and does a softmax over the tokens and picks the best token or samples a token. Making sense? And then it's going to take that token. Do I have a slide on this? There could be slides. Let me just keep saying it in English.
And then we'll translate.
And then you translate in the equations. As GPT-4 do that. You take a thought vector, right? You got the thought vector by running backwards. You feed it as the initial state. You've got a network that takes that vector and computes a softmax over the tokens. The tokens are embedded. Each token has a vector associated with it. Typically you take an inner product of a vector and the embedding of the token, and that's a score. And then you do a softmax over those scores to get a probability distribution over the tokens. Then you can either sample or you can take the best one. Right now you've got the token, you've got the first token, now you can run the RNN over that token. Right? Then you see what I've got here. Yeah. So you're generating tokens one at a time, then you're running your RNN over the generated token, and you do it again. You do a softmax again, you sample from it or take the best one, and then you keep doing it. Is that English clear enough?
And after taking the softmax and we get the token, do we still have the hidden state that pass through all the timestamps?
So you've got some initial, doing English to French, you've got some initial vector coming from the English. You do a softmax. You take that vector, use it to do a softmax, you get a token. Then you have an output RNN. It's called a sequence-to-sequence model. It's taking a sequence in and producing a sequence out. Your output RNN takes the token you generated as a first input. Then you go over that input, then you get another vector. Then you use that vector to get another input, another token, then you run over that.
So if you have like two independent like English and French distribution learners, like can you also train like a pair of encoder decoders if you have like translated text, or is it better to train them independently?
This is no. I should have said that. This is trained on translation pairs.
Okay.
So in training, I was just talking about generation. In training, you have the French, since you're given the French, all you have to do is compute the probability of each token that was in the actual French. Right? But it's a conditional probability based on the English.
Yeah.
Could you go back to the slide where you run the thing like right to left? Yes, the backward slide. So your first RNN, you run it over your English sentence, and you get this like a single hidden state as your output, right? But what is the inputs to your second RNN? Is it the English statement and this original hidden one, or like what's the
In Ilya Sutskever's paper, it was just the vector, just the thought vector.
But how can you run an RNN over one thought vector?
You just use it as the initial hidden state, feeding the.
You use it as the initial hidden state, but then what's coming in as like the X in the RNN?
So you take that and you take the English thought vector.
Sure.
And you do a softmax over your tokens. That gives you a token. Now that's an input. That token that you generated becomes an input to the RNN that's generating the French.
But again, don't you only have like one token? So then do you generate another one and then do it all over again, generate another one, do it all over again?
Right.
Okay. Thank you.
It's like specifically for the tokenization process. It's the idea that we have each of these words, then are we doing like
I
something
can tell you the modern tokenization process. I'm not sure what was. I think this might have been even words.
Sure, yeah.
The modern tokenization process is based on something called byte pair encoding.
Okay.
So in byte pair encoding, the bytes are actually little strings of characters. And I start by having a byte for every character. And then I take the most common pairs of byte codes, like the most common pair of characters, and create a byte for that pair. And then in general, I take whatever pair of tokens is most common among the pairs of tokens and add a token for that.
We need a decompressor to interpret these like
You
most
need,
common.
you need a decompressor to turn tokens. Well, each token still is representing a string. You're just building them by concatenation.
When we go from like English to French, for example.
Sorry.
When we go from like English to French, for example, if we have like the output token, would we then have to like decompress back via the same like compression mechanism, or does the compression mechanism change?
So you think of the tokens as just symbols in some vocabulary. So from the point of view of the RNN or the transformer, they're just symbols. They're embedded. They have vectors that they're embedded on. But to actually print something, you need to stick in the string, the character string that symbol represents.
So if I just delete the right to left part and use the remaining part as like, I could use that as a GPD-like model, right?
I'm sorry, I'm confused.
Like you had one that produced a thought vector and then one that took in a thought vector and produced output.
Right.
But I could just use that also to just generate random English sentences.
Well, presumably, I mean, back in the day, before the deep revolution of translation, there were these phrase-based statistical translation systems. And a super important component of that was the language model of the target language. So you always train a language model just on that language and use the language model's score as being helpful in the scoring the translation process. That disappeared here because the RNN that's generating French is learning a distribution over French as part of its model. Yeah.
Sorry, maybe I'm confused with this explanation you gave. So this is working on sentences. So we have one sentence and in the output we get another sentence which is already defined, or we are creating this sentence.
So it depends on whether we're training or actually translating.
Actually translating. Is it picking from a list of sentences that
No.
and says this is the translation?
It's doing it auto-regressively, right? So when it generates the French, it's generating the first French word or token, and the second French token, and so on. And it's generating the next one under the conditional distribution given the previous ones.
Isn't it working on sentences? Isn't it getting a whole sentence and give you a token, or it's giving you multiple tokens for each sentence?
You take a thought vector and you generate a sentence from it, one word at a time, one token at a time, until it outputs the end of sentence token.
So let's say we're doing French to English to French, and so we have a thought vector for English, and then you said from that we do a softmax, but then so is the dimension of the thought vector just the dimension of the vocabulary? Because you have to do a softmax on it, right?
So let me understand your question. So what's each French token has an embedding. There's a table that says for this token, what's the vector I'm associating with that token. So each token has an associated vector called its embedding. And when you do the softmax, you're taking an inner product, you're taking all the tokens, you've got a vector, and you're taking an inner product between the tokens embedding and your thought vector.
Okay, I see.
And typically the token embeddings are trained as part of the model parameter.
Alright, so would you say that the thought vector is sort of like language agnostic in the sense that if you were to like instead translate from like French to English, ideally you would want like a thought vector that is like sort of spatially like similar to the initial thought vector?
There's this deep question about whether our thoughts are really language specific. And if for this paper, if it's English to French, almost certainly it's very tied to English to French. But pretty quickly, Google Translate became highly multilingual. And training it multilingually improves any given language pair. So there is something across the languages that's useful.
I guess I was going to ask the same process. If we wanted to like add another like output language, like we wanted to add like English to German, would we have to like add a new like English thought compressor like that takes in the sentence and gives us a vector, or would we just add a new like thing that takes the thought vector and spits out
I'm not really up on. I'm pretty sure what's done now is you take anything in any language, and now it's a transformer, so it doesn't go to a thought vector. And so we'll get there, but the same model is used for all the language pairs. It's the same model that speaks all the languages. Yeah.
This is the kind of question a linguist would ask, but like, is there like, does there like seem to be any languages that perform differently, or is it like Romance languages do better with each other, or is there something like that where there's
Well,
like
definitely easy and hard translation pairs. So English French is like a very easy translation pair. English German is a very easy translation pair. English Japanese is a very hard translation pair. And the other problem is just sparsity of data. You get African languages where you just don't have much. So low resource.
So you said that with multilingual the translation of already had things got better, but these thought vectors aren't independent. How did that multilingual evolution affected that single translation that we had already?
Intuitively, you would like to think that the meaning is language independent. I think that was the question. So, it's a very deep philosophical question as to what the meaning of the sentence really is, independent of its language.
Mathematically, how is it possible that another language?
Well, suppose it was the case that meanings really were language independent. When I say, I got up this morning, that means the same thing in every language. then if you train all the languages together, you get a really precise, it's perfectly reasonable that, the Russian notion, like I got up this morning, is sort of, can be represented by the same vector as the English version, and you get some advantage. Alignment. What's missing in the model I just described? When you translate English to French, there's this idea, and it was fundamental to the earlier statistical phrase-based systems, that you align the words or the phrases in the source language with phrases in the target language. When I produce this word, especially for languages that reverse word order, like German or Japanese, you want to know, when I generate a word, what word in the input am I translating? Because the most naive view of translation is you just, for every word, in this language you have a word in that language. That doesn't work. But still, it's helpful to know when I'm generating this, what am I translating in the source? So there needs to be an alignment between the source and as you're generating, you want to be looking back at the source and saying, what piece of that source am I translating? This paper appeared at the same time, so this paper introduced that. And that's done with attention. And attention is the fundamental workhorse of transformers. This paper actually appeared on arXiv before Sutskever's paper. And it did it right. It introduced the attention mechanism that allowed the generation process to think about where it's coming from as it's generating. And for some reason, Sutskever's paper appeared at the conference first, a few months earlier, and got to be much more famous until transformers came along.